Welcome to section 4.1. We're talking today about starting trigonometry, and we're looking for set degrees and radians. As you go through this video, most of this will seem review. I also want you to look today at that second video on unit circles so that we can start, because tomorrow's lesson will be pretty heavy. So take a look. The intro is on page 282, and I just want to show you what they're talking about in terms of angles. There are two types. They're the angles that you did basically in geo, and I want to look at that one first. What it said is you have this angle, and in the middle of the two angles is the vertex. And then what we did is we would put our protractor on one of the sides, and normally it's this bottom side, which we call the initial side. And then you measure the angle from here to the terminal side. And we measured it, again, to the nearest degree with a protractor in geometry, but we're not using protractors at all in Algebra 2. And so this is the geo version. The Algebra 2 version puts our angle in what we call standard position. And standard position means we put it on a coordinate plane. And so as I look at my coordinate plane, my vertex will be at the origin, okay? My initial side always starts on the positive x-axis. So this right here is my initial side. And my terminal side then is wherever I end up. So I don't know, let's throw my angle down here a second. This is my terminal side, and my angle is measured from this positive x-axis in a counterclockwise direction. And so this is what we call our angle theta, where inside our angle theta would be in the geo version again right there. It's still measured though counterclockwise, and that's the biggest thing. A positive angle is counterclockwise, and negative angle is clockwise. And we don't measure our angles like in geo. We called this, let's say, A, B, and C, and we'd say angle A, B, C. We won't use any of that notation anymore. For our angle now, we are going to call that theta. And theta is what we're going to use basically for the majority of this chapter. Chapter 5, we might start calling it something slightly different, but that's the idea. You learned about radians in Algebra 2. A radian is basically another way to give you a degree. So if you're looking at 45 degrees, we can call it in terms of a radian. It's defined as the arc S of a circle intercepted by an angle, and again we're calling our angle theta, measured in the number of radians. And I want to draw some pictures for you to kind of help you figure out what a radian is. And so let me start kind of more basic with the general idea of what a radian is. And so I look at a circle that's on the coordinate plane. Okay, and basically the distance from the vertex out to the edge of the circle we know is the radius of a circle. And so our goal is to basically find an arc length, to find the length around the side of the circle that's equal in measure to this radius. So let me see if I can eyeball this a second. You're kind of looking at maybe about this length. So this is also my radius, and my goal is to make this arc length S the same thing as the radius. And if that's the case, then this would be my angle theta in radians. So our goal again, and let's just write this out, the arc length, which we call S, we want it to equal the radius of the circle. And if it does equal the radius, then my theta, my angle, is 1 radian. Okay? And so this is how they find a radian, is they somehow make this arc length the same length as the radius of the circle. So in general, let's look at how many radians then are in a circle, no matter what size the radius is. And so this picture is very, very important. We're going to ask you about placement of radians, so you should definitely know this picture. Okay, and I will emphasize that more in class too, but you should definitely know this because we're going to ask you a lot about radians. So, okay, this is my radius, right? So if here's my r, 1 radian is the arc length, that's the same distance as the radius. So if I eyeball it, this distance right here from here to here is about 1 radian. Okay, and if I go about that same distance, right here is 2 radians. And if I keep going, this length right here is about 3 radians. 4 radians is about here. Just after the 270 mark is about 5 radians. And then right here is 6 radians. And so you'll notice I still have this extra piece left over at 0 radians. Let me make that a 0 radians. I still have this extra piece. So what it's saying is that around a circle is the same thing as about 6 and 2/3. I mean, it's over the 6 radian mark. This is in your book, but again, this is completely important as we go through. You definitely want to know that. Okay. Radians, I think, is the hardest part, and it's this picture right here that's going to help. The other thing I want to show you a picture of, which is coming up, is coterminal angles. Coterminal angles. And you actually did this in Algebra 2 as well, but we only used them in degree mode, and we're going to go in radian mode here as well. Here's the idea. Coterminal angles have the same initial and terminal sides. So I'm going to draw you 2 pictures to kind of show you. Let's say I have an angle that starts here at my initial side and ends down here as my terminal side. Okay, there are 2 ways I can represent this angle. I can represent this in a positive angle. I'm going to call that angle alpha. And so this is my positive angle. Or I could represent it as a negative angle, and I'm going to call that beta, which is a negative angle. These are the same placement. What it just says is you can give them to mean either the positive version or the negative version. And so coterminal angles have the same initial and the same terminal side. But let me show you another one too that's the same thing. Let's say I have my initial side is always here on the positive axis, and my angle is here in the first quadrant. I could have this small angle, which I call alpha, is my positive angle, but I really could also have another positive angle. I could do this. I could start here and go a whole revolution around plus, and this is a beta. This is another positive angle. And you'll notice all I did is took 360 and just went a full revolution around. Well, I could do this again if I wanted. I mean, I could start here and go 1, 2, and then go here. That's still a coterminal angle as well. And so any revolution of that where you start at the initial and end at the same terminal is considered a coterminal angle. And so we're going to get to that in a little bit. I just want you to kind of have an idea of what's going on. These next 3 questions, or the next section right here, these are all no calculator questions. Okay, and so chapter 4 does still do the no calculator, but I want to give you a heads up as we're going through as to what type of things to use your calculator and you don't need your calculator for. As we look at this, complement and supplement are geometry terms, and so we want to make sure we're actually remembering those. A complement means it adds to 90 degrees. Okay, a supplement means it adds to 180 degrees. And truthfully, the way I remember it, complement comes first in the alphabet, 90 degrees comes first in the circle. Supplement comes second in the alphabet, 180 degrees comes after the 90 degrees in this circle. So those are kind of some things for you. biggest thing, what is the complement of 22 degrees? What I'm going to do is take 90 minus 22 degrees. So 90 degrees minus 22 degrees is 68 degrees. And this one I think you're pretty familiar with. That's a lot of the geometry type questions. However, it's when I start adding the radians at you that it gets a little bit more difficult. The supplement of 3 pi over 8. 180 degrees, which we're going to talk about in a second, is the same thing as pi. Pi radians. And we're going to do a unit circle and you're going to look at that, but that's something we expect that you remember from Algebra 2. So what I'm going to do is I'm going to take pi minus 3 pi over 8. Well, in order to add or subtract things, I need a common denominator. And so I'm going to multiply this pi by 8 over 8. So I have 8 pi over 8 minus 3 pi over 8, which equals 5 pi over 8. You can convert this 3 pi over 8 to a degree, find the supplement, but your answer has to be back as a radian, and you've tripled your work. So if you can keep the work in terms of radians, you're going to be much better off. But if they ask you a question in radians, your answer must be in radians. Okay. We talked a bit already about coterminal. Again, this is a no calculator question. So I'm going to look at finding 2 coterminal angles. The directions in your book say find one that's positive and one that's negative. And so I'm going to do the same thing with you just to make sure that we're okay. The idea of coterminal is it's any revolution of that angle can be a coterminal angle, and a revolution is 360 degrees. So what we're going to do is we're going to take our angle, and I'm going to add 2 pi, which is 360 degrees, and that's one revolution going in the positive direction. And I'm going to take 2 pi over 3, and I'm going to subtract 2 pi, which is going the clockwise way, and it goes back in the other direction. Again, common denominators say, okay, I need to multiply this by 3 over 3. So I have 2 pi over 3 plus 6 pi over 3 equals 8 pi over 3. And this is a positive angle. So here's my positive coterminal. In order to find my negative, I do the same thing. I need that common denominator. So I have 2 pi over 3 minus 8 pi over 3 equals negative 6 pi over 3. Oh, not 8. Let's try again. 6. No wonder this wasn't working out. Let me erase this a minute. So let me try again. If I multiply this minus 6 pi over 3, I'm still caught in the one above. 2 minus 6 is negative 4 pi over 3. So here's my negative angle. And so here's what you need to keep in mind. For coterminals, you add multiples of 360 or 2 pi to find the positive, and to find the negative, you subtract multiples of 360 or 2 pi. And I say multiples because if I didn't get a negative answer right here, I would have had to subtract another 2 pi until I get a negative. So you can keep doing revolutions forward or backwards until you get the type of answer that you want. Okay? The third one is converting between degrees and radians. This is an Algebra 2 concept. We already talked about this. 180 degrees is the same thing as pi radians. So we're going to set up a ratio, and we've done this before. If we're taking 220 degrees and we want radians, to get rid of the degrees, we put the 180 degrees on bottom so that we can cancel degrees, and pi goes on top. There are no decimals as you look at radians if you've got a pi in there. So we want to take 220 pi over 180 and reduce. I would cancel out a 0 if I'm doing this no calculator. 22 and 18, you can take 2 out of each of them, and if you take 2, you get 11 here. If you take 2, you get 9. So my answer then is 11 pi over 9. Okay? Your answers need to be as fractions with pi in it and a reduced form of your fraction. To go the other direction, they're starting me out with 15 pi over 18. If I want to get rid of the pi to get to degrees, then my pi goes in the denominator, my 180 degrees goes in the numerator, and then I can cancel my pi's. Now in this case, no calculator-wise, wow, let's look at this. Well, I can take an 18 out of the bottom and get 1. If I take an 18 out of the top, I get 10. And 15 times 10 is 150 degrees. Now you can do some multiplication. I mean, if you wanted, you could say 15 times 180 and then do long division to divide by 18. I think you'll find some little tricks along the way, though, to help you without your calculator. Okay, so that's overall a review of what we did in Algebra 2. The coterminal ones are somewhat new because we're bringing them to you in radian form, but the rest so far should have been review. If you flip the page, we're going to give you, we're going to look at 2 different formulas, and these formulas are identical to what we gave you in Algebra 2. We're talking about first arc length, and if I draw you a picture, we've kind of already talked about it, but arc length is basically the distance around the side of your circle. So here's my radius, here's my angle theta inside, this is S, which we call the arc length. So the formula for arc length is the arc length equals your angle times your radius. The biggest problem with this formula is that your theta is a radian measure. Okay? So your theta has to be in terms of radians with a pi before you can actually use that formula. The second formula for area, draw a picture again as I look at this. It's like the find the area of a pizza slice type thing. I want to know what is this whole area that it takes up of the circle. And so the area formula is 1/2 r squared times theta, and that's a multiplication, I apologize. And again, theta is a radian. So we got to keep in mind kind of as we go through. Now these formulas should look kind of familiar because again, they're the same formulas from Algebra 2. Okay, so let's take a look. They're giving you an example with Mr. Wilcox. Okay, so he's racing on a circle track with a radius of 50 meters. So let's do a small little picture. He's on this circle racetrack. This radius here is 50. Okay, 50 meters is kind of important. In 15 seconds, he covered 3/4 of the track. Okay, well, if I talk about it covering 3/4, here's 1/4, 2/4, 3/4. So after 15 seconds, Mr. Wilcox is down here. Now the question is how many degrees or radians. We need it in terms of radians in order to be able to figure out our formulas. Well, if I look at this, a whole circle is 2 pi, but he went 3/4 of that. So I have 6 pi over 4, which is 3 pi over 2. This is my angle. Now that's one way to do it. You could have also said, well, I know in degrees, this is 90, 180, 270, and I could have said 270 degrees times pi over 180 and converted it that way. You still would have gotten 3 pi over 2. So it's kind of up to you, but either way our angle is 3 pi over 2. How far has he traveled means what is the arc length. So I used my arc length formula. My arc length is my angle times my radius. So 3 pi over 2 times 50 meters. Well, 50 divided by 2 is 25. 25 times 3 is 75 pi. The only problem, and I could say meters, the only problem is I don't really know this distance, so let's change it to a decimal. This is about 235.62 meters. You do have to have that label. okay? And you could give it to me either way if they say exactly or approximate, but the label has to be there no matter what, okay? So far we know that the angle traveled is 3 pi over 2. Keep that in mind as I move along. The next question says, and let me put my angle back up there, 3 pi over 2, and my radius we said was 50 meters as I'm going through this with you. What is the area of the sector of the track? So they want the area. Okay, well, according to our formula, area is 1/2 r squared times theta. So plug and chug. 1/2 times 50 squared times 3 pi over 2. Okay? Now, you could go calculator, you could try not, it's up to you. I can tell you that 50 squared, though, is 2,500 times 3 pi over 2. Either way, you end up getting about 1,875 pi meters squared because it's area. So that's one way to write it. Again, I don't know that area, so I'm going to change it to a decimal. 5,890.49 meters squared. Most of the arc length and area of the sector questions, we're going to let you change to decimals. So these are probably more calculator-based questions. If they're no calculator, we probably won't be giving you 2,500. We'll give you more like something like 49 or 64. That's a little bit easier to work with. Okay? These last two things, linear speed and angular speed, are formulas that you also need to know. And I'm going to give you those. Linear speed, they call this V. This linear speed is found by taking the arc length and dividing it by time. It's basically like a miles per hour type thing. It's a speed. So you're talking the distance divided by time. It's like a miles per hour, or meters, in this case, per second, as we go through, because we found above the arc length was 75 pi. And we knew that this time was 15 seconds. I probably need to throw meters on here. And so you can see that the speed is meters per second, which if you've taken physics at all, you know it is a perfectly good quantifier for a speed. But if I reduce this, you end up getting 5 pi meters per second, or you can approximate this to 15.71 meters per second. Okay, so we would take either of these. It depends, again, calculator, which is this one, or no calculator, this one. Okay, so linear speed is just speed, miles per second, or miles per hour, meters per second, anything like that. An angular speed is slightly different, because an angular speed, which we call, it looks kind of like the infinity sign, but it's actually a W, okay, is basically your angle divided by your time. So it's basically asking you, how quickly did you make the curve? I mean, like, how quickly did you turn? Now, our angle is theta, and don't forget, theta is in radians, divided by our time. Okay, well, our angle was 3 pi over 2. Our time is 15. And let me go through dividing a fraction by a number. Dividing by a number is the same thing as multiplying by its reciprocal. So you have 3 pi over 30, which is pi over 10. And if I need a label, we said it's radians, right? Radians per 15 seconds. So radians per second. Okay, you could multiply that out. No, I don't have that decimal, but this is the idea. Angular has to have an angular measure, a radian per second. Linear speed has to have a meters per second. And again, these two formulas you should kind of know. We're going to practice a little bit with them on the homework. But I think, again, if you've had physics or anything, speed should say how far you went divided by your time. Your angular speed says how much of an angle did you go divided by time. So that's section 4.1. Again, the majority of 4.1 is the review. What you will also want to do is watch the next video though, and I put it right in today's lesson right on my website. But I want to talk about getting degrees and radians on a unit circle. So you'll have a blank unit circle in your packet. Please, again, make sure that you fill that out today as well. Thank you for watching. And again, don't forget that second video.